This video might not be as useful as I had originally intended, but since I did put those problems in the packet, I thought I should at least explain where you should be at some point. Now, let me explain that what happened was the original problems, what I didn't get in there was that you were supposed to, and it was in red, so when I transferred it didn't show up, but what you were supposed to show on the sheet was that you don't have to solve cubic functions, as I'm going to get to a little bit later. But there was one more thing on this sheet that when I photocopied it, it did not transfer as I had hoped. But you were supposed to show that you weren't actually expected to solve everything about these equations. You were supposed to get things set up so that you would understand them, but not necessarily solve a cubic equation. And I'm not a math teacher, quite obviously, so I'm not going to teach how to solve cubic equations. If someone wants to do it on their own, that is their prerogative, but I am not getting involved in the teaching of solving cubic equations. It's challenging enough for me for the quadratic, so we'll just stick with that. Now, this was one of the problems on the packet. This was number 1 on page 10. And again, it was just with the intention of setting up a proper ice table for it, not actually solving the equilibrium concentration. So I'll lead you through to the point that you were expected to do, which was a little bit misleading if you did jump ahead, which hopefully you didn't. But if you did, because I know some people had expressed that they had gone ahead, well, I didn't mean to confuse anyone. But I did photocopy this and not be aware of everything that should have transferred. I guess I should point out that my printer isn't a color printer. So when you put something in red, it's not going to print out on a black and white printer. So, lesson learned. But 0.6 moles of nitrogen monoxide and 0.750 moles of oxygen are placed in an empty 2-liter flask. The system is allowed to establish equilibrium. What will the equilibrium concentration of each species be in the flask? Okay, so we set up our ice table, and what do we know? We know that I'm given an equilibrium constant for actually this reaction. And in this case, it's very confusing because I have my product with 0 concentration at the start. And I have my reactants with a concentration at the start. Now, my Kc would be a different value. It would be the inverse if I flip this around. But since I'm given this Kc, I'm going to have to solve it proceeding this way. And again, that's only because I was given the equation as it appears, and I was given my equilibrium constant for this reaction, which is nitrogen dioxide turning into nitrogen monoxide and oxygen. So my reactant starts with a 0 molar concentration, and then my products, I have 0.6 in 2 liters, so 0.3 molar, and have 0.75 in 2 liters, and that's 0.375. Now, unlike the other ice charts we've seen, in this case, my reactant has to increase concentration. You can't decrease from 0. And these two will decrease because there's no other thing they can do besides decrease if I'm going to increase my nitrogen dioxide concentration. So at equilibrium, this should be fairly self-explanatory what's going on. The intention here is to see different ways that these reactions can proceed. Now, if I had gone the other way, and if I had started with a concentration of nitrogen monoxide and oxygen, I would end up with the same concentrations if these are what I'm putting in. It's just my equilibrium constant would be reversed because a different setup for the law of mass action equation. So in order to find equilibrium concentrations, again, our Kc is 0.50. From the ice table, I've determined what my concentrations would be, and then all that you were actually expected to do was set up the equation. There is the equation. Now you see we will have an x squared. We're going to multiply that by an x. It's messy. You have a cubic formula that you have to factor. We're not going to go that far. It was just to set up this equation was how far you needed to go. The thinking was it's good practice, it's really intimidating, and then when we do simpler equations, it shouldn't quite seem so bad. The second one, same thing. Now, this one you actually could do something. We have concentrations at an equilibrium. So you could actually proceed to setting this up and finding an equilibrium constant. And that means that I have an opportunity to plug all of these in. So my concentration of oxygen, my concentration of carbon monoxide, and my concentration of carbon dioxide would all be plugged in. All right. Once we have the equilibrium constant calculated, now I need to think about what happened in my reaction. So it says that I add carbon monoxide. So I'm actually spiking this, which is going to push my reaction. I've increased concentration here. It's going to push my reaction to the left. So this is going to actually decrease. This is going to increase, which means when I set up my ice table, I got the animation wrong, but when I set up my ice table, the concentration of carbon monoxide will decrease. It will decrease because it's going to also be hitting oxygen, and it's going to boost the concentration of carbon dioxide due to Le Chatelier's principle. We've put a stress on the equilibrium. Now, this is my equilibrium constant that I calculated previously. These are still my products. However, they are both going to decrease in value, and this is going to carbon monoxide is going to decrease double what oxygen decreases, and then carbon dioxide is going to increase. Now, beyond this, you see we have a cubic formula, and we do not need to worry about factoring that. The idea was just to get that problem set up in the right way. Now, the last one, this one is workable. This one we can do. We're going to look at pressure. Now, what you need to realize is that pressure is directly proportional to the concentration of a gas. If I increase concentration, I increase the pressure of the gas. If I increase pressure, I also increase concentration. Also, these KEQs, they are unitless. They do not have any units associated with them. So therefore, if I use something like atmospheres and I feed this through my equilibrium constant equation, my units at the end, since this is unitless, my units at the end would be atmospheres. So taking a look at this, actually that shouldn't be concentration, that should be pressure. It should be P with the subscript Cl2, but I don't think I have that capability with PowerPoint. So that would be pressure of chlorine and pressure of monoatomic chlorine, which happens when you heat this at a high temperature. I didn't actually read this problem, but what this problem says is chlorine gas undergoes homolytic, so it breaks apart into chlorine atoms at 1,000 degrees Celsius. The pressure constant at 1,100 degrees Celsius for this process is 1.13 times 10 to the negative fourth. Again, a unitless number. If a sample with initial chlorine gas pressure of 0.5 atmospheres was allowed to reach equilibrium, what is the total pressure in the flask? So, when we start out, all of my pressure comes from chlorine. None of it comes from monoatomic chlorine. The pressure of this will have to go down because I'm making chlorine atoms from chlorine molecules. If every mole of chlorine gas will turn into 2 moles of chlorine atoms, which means in equilibrium, this declines by x and this increases by 2x. Now this I can put into my equilibrium constant equation. I'm going to put what I need on the different sides. I'm going to do my algebra. This is what we had before. The equilibrium would be my reactant. My reactant on the bottom, chlorine, and my product on the top. So this would be 2x squared, because its coefficient is 2, over 0.500 minus x. All of that is done. I end up getting another quadratic formula, or an equation that I can enter into the quadratic formula. Now, I didn't actually do the whole mathematical thing, but this is your A, this is your B, this is your C. And if you plug it into the quadratic formula, a lot of people know the song. You can go ahead and do that, and then we end up getting two possible values. Now, look, one is a positive, one is a negative. You can't have a negative pressure. If you had a negative pressure, that would mean that my pressure increased for no apparent reason because my concentration of chlorine increased. You can't do that. So I only have one logical answer here, which is 0.0037. This would be 0.0037 atmospheres because this unit was atmospheres. Therefore, all of these units are atmospheres because this is a unitless number. In order to calculate what the total pressure would be, the equilibrium pressure, as my ICE table said, is 0.500 minus my X value, which I just calculated, which 4.96 atmospheres of pressure in the final volume comes from chlorine, diatomic chlorine gas. And 0.0074 atmospheres comes from monoatomic chlorine gas because its original pressure was 0 and we've gone up to 2x, which we calculate our x as 0.0037 and 0.0074 atmospheres. Now, total pressure, Dalton's law of partial pressures, we add these up, we get 0.503 atmospheres. That would be the total pressure. So again, pressure, concentration, they can be equivalent when we're talking about gases. They wouldn't be equivalent for solutes in solution because they don't get more concentrated. They're in water. Water is incompressible, or a liquid is incompressible. This is only valid for gases, but I just wanted to make sure this one I actually wanted to make sure you had an opportunity to see, and I don't think there was anything that didn't print as the other papers had. So that concludes this presentation, and we will move on to solubility product constants.